In this video, I'm going to go over the solutions to problem set 5.1 for questions 7 through 11 found on page 174 and 175. So question 7 I've summarized. This is kind of an odd little question. It says the mass of the burner and its content is measured before and after the experiment. The thermometer is read before and after the experiment. What are the expected results? And they don't indicate that this is going with any experiment that they've described in the print above that. So since it says burner and contents, I'm assuming it's not a Bunsen burner like we use. It's a burner with fuel in it, so like an alcohol burner or something. And your hint is that it says it's content. So since there's something in it, you can assume that that's fuel that's going to be burned. So they want to know what the mass before and after the experiment would be, and then they say the thermometer is read before and after the experiment. So if you understand the question, it's actually a very simple question. If you burn some fuel, your mass should decrease and your thermometer should increase. So that's the answer they're looking for, is that A, the mass decreases while temperature increases. So that's what they were looking for on number 7. Question number 8, they're referring to the experimental arrangement in figure 5.7, which is on the previous page on 173. And you see a little alcohol burner, a burner with ethanol as the fuel, and it's burning below a container of water, a copper calorimeter with water and a thermometer in it, and then an insulating card as the cover. So again, this is probably the setup they were referring to in question 7. They just didn't bother telling us that. But it says the experimental arrangement in figure 5.7 is used to determine the enthalpy of combustion of an alcohol. Which of the following would lead to an experiment result which is less exothermic than the literature value? So as you look at these three, what you have to keep in mind is we're determining delta H based on M times C times delta T. C is not going to change, so really the question as we look at these three is, did any of them affect M or delta T? And if they did, an increase in either M or delta T, or our measured M and delta T, would increase the delta H, whereas if we had a decrease in our measured M or delta T, it would also decrease delta H. So heat loss from a copper calorimeter, that's going to change our delta T, and that's definitely going to decrease our value. So that would give us a less exothermic or a smaller value than what we'd expect. So a big yes for number 1. Evaporation of alcohol. If some of the alcohol evaporates, that means it doesn't all burn. So there's going to be less temperature increase. It also means our mass is going to be less than it should be. So this is going to affect it twofold. But definitely it's going to decrease the temperature change and potentially decrease the mass. So yes, it also will decrease delta H. The third one, the thermometer touching the bottom, this is actually going to elevate our temperature or make it hotter than what the water is, because it's measuring the direct source of heat there where it's coming into the calorimeter. So this one would actually inflate our value. So for number 8, 1 and 2 only are going to affect it, or letter A. Number 9 talks about an experiment done, and bottom line is that the experimental value you got from your calorimeter was negative 2100 plus or minus 200 kilojoules per mole, and the accepted literature value is minus 2676. So at best, your value was 23 minus 2300, which is still 376 kilojoules per mole off from the literature value. So which of these would account for the difference between the two values? Number 1, the random measurement errors. By definition, random measurement or random errors can either inflate or deflate. It's when you're looking at equipment, like when you look at your graduated cylinder and you're estimating where the meniscus is, there's an equal chance of you estimating high or low. A systematic error is going to give you a consistently high or low value because there's a mistake in what you're doing. But a random error is just that. It has a random chance of being too high, too low, or right on the mark. So random measurement errors would not account for this. But incomplete combustion, that definitely would give you a lower value because less heat would be produced since not all of the reactant combusted. And then heat loss is always the number one source of air in a calorimeter experiment. So 2 and 3 definitely would play a role in this. So number 9C would be 2 and 3 only. Question number 10 describes a calorimeter experiment where 1.1 gram of glucose, which is C6H12O6, is completely burned in a copper calorimeter. Temperature of the water increased from 25.85 to 36.5. And then they give you information for both the mass and specific heat of water and of copper. So the thought here is that you can use MCAT, take the 200 times 4.18 times the temperature change of 10.65, and come up with an energy change or an enthalpy change for the water equal to 8903.5. But then because you have the copper calorimeter, which this is actually fairly common practice, you can also calculate the energy absorbed by the copper because we know metals are good conductors of heat. So instead of using a well-insulated container, you go ahead and use the copper and then calculate the heat it would absorb as well. So 120 times the 0.385, and then we'd assume the same temperature change since it's transferring the heat to water. And I get 9395, I'm sorry, I get 492 for the copper, and when I add them together, I get the 9395, or 9.4 kilojoules. So that's my delta H when I take into account both the water and the copper. If you did just the water, not a big deal. So then the second part of this, though, is that I need to go ahead and come up with this in kilojoules per mole. So now I have to take my 1.10 grams of glucose, find that its molar mass is 180.18. So we're actually talking 0.00611 moles. And when I take my 9.4 and divide by the 0.00611 moles, then our enthalpy becomes negative 1540 kilojoules per mole. And then finally you were asked to draw, oops, I don't know if I can extend my page a little here. Yes, I can. So then for part B, you were asked to go ahead and draw the enthalpy diagram for this. So your enthalpy diagram, you should mark that it's energy versus time. Make sure you label your axes. And you could just draw the reactant to the product like this. Or if you prefer the way I do it, you could show that there's activation energy. And then if you want to be really fancy, you could include that this is the delta H value of negative 1540. So either enthalpy diagram is fine. Just make sure you label axes. And then I usually label the reactant and product, although I think it's pretty obvious you start with reactants and end with products. Number 11, the heat released from the combustion of 0.0500 grams of white phosphorus, so just P, increases the temperature of 150 grams and 0.00. They're giving you all those 0.00 so you can figure out your sig figs. So that's the mass of water, which is in our calorimeter, and its temperature increased from 25 to 31.5, or a 6.5 degree temperature change. So they want to know the enthalpy value for the combustion of phosphorus. So that means I need to have this in kilojoules per mole. So I'm going to find the delta H for the water change, so 150 times the 4.18 times the 6.5. And even though I've got 5 sig figs out of my mass, my temperature is only going to give me 2 sig figs. So when I go ahead and crunch this in, I come up with 4,075.5. But again, I only have 2 sig figs, so it's really 4,100, or 4.1 kilojoules is what we're talking here, because this was joules up here. And then I need to go ahead and change my 0.0500 grams of phosphorus to moles, and 1 mole of phosphorus is 30.97 grams. So we're talking 0.00161 moles of phosphorus. And now when I take my 4.11 kilojoules divided by the 0.00161 moles, I get a heat of combustion using 2 sig figs of negative 2,500 kilojoules per mole.